A number exists in physics that no one can explain. A number so absurdly wrong, it has been called the worst prediction in the history of science. This number differs from observation by a factor of 10 to the 120th power. Perspective helps here. 10 to the 120 exceeds the number of atoms in the observable universe, exceeds the number of seconds that have passed since time began, exceeds any number encountered in any other field of science by margins that defy comprehension. Physicists have checked and rechecked this calculation for decades, and the mathematics holds up. The physics underlying it remains well established. The answer still comes out wrong by 120 orders of magnitude. What the calculation concerns is empty space, the vacuum, the nothing between atoms that make up everything. According to quantum field theory, this vacuum seethes with energy, a residual quantum hum impossible to eliminate even in principle. This energy, called zero-point energy or vacuum energy, should produce gravitational effects, should curve space-time, should influence how the cosmos expands. Comparing how much energy the vacuum should contain to what observations actually reveal produces a disagreement so vast that calling it a discrepancy feels inadequate. This is the Vacuum Catastrophe, and it stands as one of the deepest unsolved problems in all of physics. By the end of this video, you will understand what vacuum energy is and why quantum mechanics demands it exists. You will see why this energy should gravitate and what that would mean for the cosmos. You will learn how astronomers measured the actual vacuum energy through observations of distant supernovae and the cosmic microwave background. And you will confront the 120 order of magnitude gap that has puzzled physicists for decades. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Starting with what vacuum means in physics matters, because everyday meaning and physics meaning diverge in important ways. Everyday language treats vacuum as empty, devoid of matter, containing nothing. A vacuum chamber holds no air. Space between stars gets called the vacuum of space. Absence, nothingness, zero, these associations follow the word. Quantum mechanics changed this picture entirely. Quantum field theory, the framework describing particles and forces at fundamental levels, treats the vacuum as anything but empty. What it describes is the lowest energy state of quantum fields filling all of space. And this lowest energy state does not equal zero. Picture a quantum harmonic oscillator, the simplest quantum system, a particle in a potential, well oscillating back and forth. Classical physics allows removing all energy from such a system, bringing it to complete rest. Quantum mechanics forbids this because the uncertainty principle stands in the way. The lowest energy state, the ground state, retains energy. This residual energy carries the name zero-point energy. A single oscillator has zero-point energy equal to 1/2 times Planck's constant times the frequency. The formula runs E equals 1/2 h bar omega, where h bar represents the reduced Planck constant and omega represents angular frequency. Quantum field theory treats every point in space as containing quantum oscillators, one for each mode of each field. Oscillators at every frequency populate the electromagnetic field. The electron field contributes its own oscillators. Every fundamental field adds to the total, and each of these oscillators possesses a ground state with zero-point energy. Add all these contributions together and you get the total vacuum energy. And here is where the problem begins. Adding contributions from all frequencies produces a sum that diverges. It runs to infinity. Infinite answers in physics usually signal something wrong with the calculation or application beyond the theory's domain of validity. Physicists handle this by introducing a cutoff, a maximum frequency or energy beyond which counting stops. Trust in the theory ends at some scale, so contributions from higher scales get ignored. The question becomes where to place that cutoff. What energy scale marks where quantum field theory breaks down? Werner Heisenberg discovered the uncertainty principle, which states you cannot know both position and momentum of a particle with arbitrary precision simultaneously. Knowing a particle sits exactly at rest means knowing its momentum exactly at zero, while also constraining position because position would not change. The uncertainty principle forbids this combination. For a particle in a potential well, an oscillator, direct consequences follow. Zero energy does not describe the lowest state. The particle still jiggles with irreducible motion that cannot be eliminated. This residual motion carries zero-point energy. The formula runs simple yet carries weight. A harmonic oscillator with angular frequency omega has ground state energy of 1/2 times h bar times omega. Not zero, always positive, always present. Measurable consequences flow from this, not theoretical abstraction. The Casimir effect demonstrates one consequence. Another appears in the Lambda shift, a tiny splitting in hydrogen energy levels that counted among quantum electrodynamics' early triumphs. Explaining the Lambda shift requires accounting for vacuum fluctuations. Extending to quantum field theory, a field, like the electromagnetic field, decomposes into modes, each behaving like an independent harmonic oscillator, characterized by wavelength, or equivalently, frequency. Every mode carries zero-point energy equal to 1/2 h bar times its frequency. Higher frequency modes contribute more zero-point energy than lower frequency modes contribute. How many modes exist? Infinitely many in principle, at every frequency, from arbitrarily low to arbitrarily high. Adding them all yields an infinite sum. Physics handles infinities through regularization and renormalization, techniques separating meaningful finite parts from divergent infinities. Ordinary quantum field theory, without gravity, absorbs the infinite vacuum energy into a redefinition of energy's zero point, shifting all energies by a constant that affects no prediction, since only energy differences matter. Gravity breaks this approach. Gravity responds to absolute energy density. The infinite vacuum energy, or the large finite energy surviving after introducing a cutoff, curves space-time. Shifting it away becomes impossible. The natural answer points to the Planck scale, the energy scale where quantum mechanics and gravity both become important simultaneously, where current theories expect breakdown and replacement by quantum gravity, whatever form that takes. Three fundamental constants define the Planck scale: the speed of light, Planck's constant, and Newton's gravitational constant. Combining them in particular ways yields natural units for length, time, and mass. Approximately 1.616 times 10 to the negative 35 meters defines the Planck length. About 6.36 times 10 to the negative 34 inches. Inconceivably small captures this scale. A proton spans about 10 to the negative 15 meters, making the Planck length 20 orders of magnitude smaller. Approximately 5.39 times 10 to the negative 44 seconds gives the Planck time, what light needs to cross one Planck length. About 10 to the 18 giga-electron volts, or roughly 10 to the 19 GeV, corresponds to the Planck energy. This vastly exceeds particle accelerator energies. The Large Hadron Collider reaches about 10 to the 4 GeV, putting the Planck scale 15 orders of magnitude higher. Placing the cutoff at the Planck scale and summing zero-point energies from modes below it produces vacuum energy density of order 10 to the 18 GeV to the fourth power. Standard units translate this into an enormous number. That is the theoretical prediction. Vacuum energy density should run on the order of Planck scale to the fourth power. Now, compare this to what cosmic observations actually reveal. Cosmological measurements, particularly from the Planck satellite studying the cosmic microwave background, combined with observations of distant supernovae and large-scale structure, reveal the actual energy density associated with accelerating expansion. Using a Hubble constant of approximately 67.4 kilometers per second per megaparsec, with a dark energy density parameter around 0.685, the implied vacuum energy density comes to approximately 5.8 times 10 to the negative 27 kilograms per cubic meter, about 3.7 times 10 to the negative 28 pounds per cubic foot. Converting to energy density gives approximately 5.2 times 10 to the negative 10 joules per cubic meter, roughly 3.3 kilo-electron volts per cubic centimeter. Expressed as energy scale to the fourth power, the observed value corresponds to roughly 10 to the negative 3 electron volts to the fourth power, about 10 to the negative 12 GeV to the fourth power. A cutoff represents the energy scale above which we do not trust our theory. Physics operates in regimes of validity. Newtonian mechanics works at everyday scales, but fails at relativistic speeds. Classical physics works at macroscopic scales, but fails for atoms. Every theory has limits. Quantum field theory should break down at or before the Planck scale, where quantum effects and gravitational effects become equally important, where separating physics into quantum mechanics over here and general relativity over there can no longer hold. About 1.22 times 10 to the 19 GeV defines the Planck energy, unimaginably high by particle physics standards. The highest energy particle accelerator, the Large Hadron Collider, reaches about 14 TeV, which equals 14,000 GeV, putting the Planck scale 15 orders of magnitude beyond reach. Using the Planck scale as cutoff produces the famous 120 orders of magnitude discrepancy. Suppose you take a conservative stance and argue new physics might appear at lower scales, that quantum field theory might break down before reaching Planck scale. Where else might the cutoff belong? Around 250 GeV sits the electroweak scale, where the Higgs mechanism gives particles mass. Colliders have probed this scale, and physics here remains well understood. An electroweak cutoff gives vacuum energy density of order 250 GeV to the fourth power, smaller than the Planck scale prediction by a factor of 10 to the 18 to the fourth power, roughly 10 to the 72. That reduces the discrepancy from 120 orders to roughly 50 orders of magnitude. Still an enormous mismatch, still utterly inexplicable. Going lower to the QCD scale, around 200 MeV, where the strong force becomes strong, gives vacuum energy density of order 200 MeV to the fourth power, reducing the discrepancy to roughly 40 orders of magnitude. Still catastrophic, still beyond any reasonable fine-tuning. Getting the calculation to agree with observation requires using a cutoff around 10 to the negative 3 electron volts. But no known physics changes at that scale. It appears arbitrary. Compare theoretical prediction to observed value directly. Planck scale prediction gives vacuum energy density of order 10 to the 18 GeV to the fourth power. Observed value runs order 10 to the negative 12 GeV to the fourth power. That ratio equals 10 to the 18 divided by 10 to the negative 12, which gives 10 to the 30. Comparing fourth powers of energy scales means the ratio in energy density becomes 10 to the 30 to the fourth power, equaling 10 to the 120. The theoretical prediction overshoots observation by 120 orders of magnitude. Pause and think about that. Not 120%. Not a factor of 120. Not 120 orders of magnitude in some abstract mathematical sense, carrying no physical consequence. This is 120 orders of magnitude in a quantity determining the fate of the cosmos. Feeling what 10 to the 120 means requires effort. Comparing 1 second to 10 to the 120 seconds yields a span of approximately 3 times 10 to the 112 years. The universe measures roughly 14 billion years old, about 10 to the 10 years. The ratio of 10 to the 120 seconds to the universe's age itself runs about 10 to the 102, another unfathomably large number. No other prediction in physics misses by this margin. Quantum electrodynamics predicts the electron's magnetic moment to better than 1 part in a trillion. Standard model particle physics makes predictions routinely confirmed to many decimal places. These same frameworks, applied to vacuum energy, produce an answer off by a factor larger than any number encountered in any other physical context. This is why the word catastrophe applies. The term carries no hyperbole. Human terms help with the observed vacuum energy density. The value of 5.8 times 10 to the negative 27 kilograms per cubic meter corresponds to only a few proton masses per cubic meter. A proton carries mass of about 1.67 times 10 to the negative 27 kilograms, making this density roughly 3 to 4 protons worth of mass equivalent energy spread across each cubic meter of space. Air at sea level measures about 1.2 kilograms per cubic meter for comparison. Observed vacuum energy density runs about 26 orders of magnitude smaller than air density. Extraordinarily dilute describes it well. Yet, this tiny density, spread across cosmic vastness, dominates the universe's energy budget today. Feeling the magnitude of 10 to the 120 requires more approaches. If you possessed 10 to the 120 grains of sand, each 1 millimeter across, the pile would extend far beyond the observable universe. Roughly 10 to the 80 atoms populate the observable universe, meaning you would need to fill 10 to the 40 observable universes with atoms to reach 10 to the 120 objects. Counting one number per second, reaching 10 to the 120 would take 10 to the 120 seconds. The universe measures about 4 times 10 to the 17 seconds old, requiring roughly 10 to the 102 universe ages to finish counting. If 10 to the 120 represented dollars and the entire global economy, roughly 10 to the 14 dollars per year, devoted itself to spending them, the task would take 10 to the 106 years, about 10 to the 96 times the age of the universe. No quantity in any other science field involves numbers remotely this large or mismatches remotely this severe. The gravitational constant carries precision to about 1 part in 10 to the 5. The fine structure constant carries precision to about 1 part in 10 to the 10. The electron magnetic moment agrees with calculation to about 1 part in 10 to the 12. These represent physics precision achievements. The vacuum catastrophe constitutes an imprecision of 1 part in 10 to the 120. It dwarfs every other discrepancy. This is not a rounding error or small overlooked correction. Represents a failure of prediction so complete it challenges the foundations of how we combine quantum mechanics and gravity. When I first worked through these numbers, I kept thinking I must have made an error. Surely the discrepancy could not reach this magnitude. Checking and rechecking confirmed the numbers. The discrepancy stands real. Why this matters might puzzle you at first. Ordinary quantum field theory, without gravity, treats the absolute value of vacuum energy as irrelevant. Energy differences matter, not absolute levels. Adding or subtracting a constant from all energies changes no prediction. Temperature scales offer an analogy. Measuring in Celsius, Fahrenheit or Kelvin places 0 differently in each, but the physics remains the same. Temperature differences carry meaning, not absolute values. Gravity changes everything. General relativity, Einstein's theory of gravity, treats energy density as a source of space-time curvature. More energy in a region means more space-time curvature. Unlike ordinary physics, where only energy differences matter, gravity responds to absolute energy density values. This means vacuum energy, whatever its value, should affect space-time curvature. If the vacuum has energy, the vacuum should gravitate. Empty space should pull on itself. Einstein actually included a term for this in his equations. In 1917, applying general relativity to cosmology, he added what he called the cosmological constant, denoted by Greek letter lambda. Einstein's motivation differed from modern understanding. He wanted a static universe, neither expanding nor contracting, and found his equations without the cosmological constant did not permit this. Adding lambda provided repulsive effect that could balance gravitational attraction, allowing a static solution. Within a decade, Edwin Hubble's observations showed the universe is not static but expanding. Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. The mathematics remained valid, though. A cosmological constant in Einstein's equations equals, mathematically, a uniform energy density filling all space, carrying a peculiar property: negative pressure. This negative pressure matters enormously. General relativity has both energy density and pressure contributing to gravitational effects. Ordinary matter carries positive pressure, with both density and pressure contributing to attraction. The cosmological constant carries negative pressure, and, working through the equations, shows this negative pressure dominating, causing repulsion rather than attraction. This explains why a positive cosmological constant drives accelerating expansion. The universe expands faster and faster, with distant galaxies receding at ever-increasing speeds. General relativity treats energy and matter as sources of space-time curvature with elegant mathematical comps. Statement: the Einstein tensor describing space-time geometry equals a constant times the stress-energy tensor describing energy and momentum distribution. For ordinary matter, the stress-energy tensor describes mass density, pressure, momentum flow, and stresses. A star concentrates mass in a region, creating curvature around it. A planet orbits in that curved space-time, following the straightest possible path through curved geometry. Vacuum energy enters the stress-energy tensor as uniform energy density filling all space. Unlike ordinary matter clumping into structures, vacuum energy remains the same everywhere, its density unchanged whether the universe expands or contracts. Pressure associates with this energy density. For vacuum energy described by a cosmological constant, pressure runs negative, equaling -1 times energy density. This breaks from ordinary gases with positive pressure. Vacuum energy carries negative pressure. The equation of state parameter W relates pressure to density. Ordinary matter at rest has W equaling 0, meaning no pressure. Radiation has W equaling 1/3. A cosmological constant has W equaling -1. General relativity has both energy density and pressure contributing to gravitational effects. The combination, mattering for cosmic expansion acceleration, involves density plus 3 times pressure. For ordinary matter, this runs positive, leading to attractive gravity and deceleration. For a cosmological constant, density plus 3 times negative density equals negative 2 times density, running negative. This negative combination produces repulsive gravitational effects. A cosmological constant does not pull things together, but pushes them apart. Positive vacuum energy drives accelerating expansion. Larger vacuum energy density means stronger repulsion and faster acceleration. Vacuum energy at the Planck scale would produce acceleration so extreme that expansion would dominate from the earliest instance, preventing any structure from forming. Observed vacuum energy runs so small, its effects only became dominant recently in cosmic history, after galaxies had formed and evolved for billions of years. The timing raises questions. Why should vacuum energy become dominant approximately now, when observers exist to notice? This coincidence sometimes carries the name Cosmological coincidence problem, another aspect of the puzzle surrounding dark energy. Einstein's relationship with the cosmological constant tells a story worth exploring. In 1917, Einstein developed the first cosmological model based on general relativity. He wanted a static universe, neither expanding nor contracting, matching the astronomical observations of his era. Stars and galaxies appeared fixed, not rushing toward or away from us. The problem was that general relativity without modification did not permit a static universe. Gravity attracts. A universe filled with matter should either expand or collapse, with no natural equilibrium. Einstein's solution added a new term to his equations, the cosmological constant lambda, acting as repulsive force, balancing gravitational attraction and allowing a static solution. Observations within a decade began suggesting the universe was not static. By the late 1920s, Edwin Hubble had measured redshifts of distant galaxies, showing they were receding. Georges Lemaitre had proposed universal expansion. The cosmological constant lost its original purpose. Einstein reportedly told George Gamow that introducing it counted as his greatest blunder, and he abandoned it. For decades afterward, the cosmological constant received treatment as a curiosity. Most cosmologists set it to 0 for simplicity. Why include an extra term if observations did not require it? The theoretical problem was already recognized, though. Quantum field theory suggested vacuum energy should exist and act like a cosmological constant. But observations stayed consistent with 0, making the question why it was 0 rather than why it had some particular small value. The 1998 supernova results changed everything. The cosmological constant was not 0. Einstein's blunder, his regretted equation addition, turned out to describe something real. History's judgment of Einstein's greatest blunder has itself undergone revision. Adding the term might have been unnecessary for his purpose, but the term represents real physics. The irony runs deep. The 1960s made the connection between quantum vacuum energy and cosmological constant explicit, particularly through Soviet physicist Yakov Zeldovich. He pointed out that quantum field theory, predicts vacuum energy, that this energy should gravitate, and that it would act like Einstein's cosmological constant. Zeldovich also recognized the problem. Even conservative vacuum energy estimates vastly exceeded any plausible cosmological value. The mismatch was apparent decades before precision cosmology made it acute. Through the 1970s and 1980s, the cosmological constant problem gained recognition as a fundamental puzzle. By 1989, Steven Weinberg published a landmark review that became the standard reference. Weinberg surveyed possible solutions from symmetry-based cancellations to anthropic selection and found none fully satisfactory. Most cosmologists at that time assumed the cosmological constant equaled exactly zero. Some unknown mechanism, perhaps related to an undiscovered symmetry, must be cancelling vacuum energy precisely. The problem was explaining why it was zero, not why it had some particular small value. Everything changed in 1998 and 1999. Two independent astronomer teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying distant Type 1a supernovae. These supernovae serve as standard candles, explosions of such predictable brightness that their apparent dimness reveals their distance. Both teams found the same surprising result. Distant supernovae appeared dimmer than expected, meaning they were farther away than expected, meaning expansion had not slowed as much as expected. It had sped up. Accelerating expansion matches exactly what a positive cosmological constant would produce. Observations implied roughly 2/3 of the universe's energy budget consists of something acting like a cosmological constant, something driving galaxies apart at accelerating rate. This component received the name dark energy, not because we understand what it is, but precisely because we do not. Dark energy serves as placeholder name for whatever causes the acceleration. The three lead researchers received the 2011 Nobel Prize in Physics for this discovery. Accelerating expansion discovery launched an era of precision cosmology aimed at measuring dark energy properties as accurately as possible. The Planck satellite, a European Space Agency mission operating from 2009 to 2013, provided the most detailed cosmic microwave background map ever made. This radiation, emitted when the universe was about 380,000 years old, carries imprints of universal composition and geometry. From Planck data, combined with other observations, cosmologists derived standard Lambda CDM model parameters. Lambda stands for cosmological constant. CDM stands for cold dark matter. Together with ordinary matter, these components describe the universe's energy budget. The Planck 2018 results, considered definitive analysis of that mission's data, give Hubble constant of approximately 67.4 kilometers per second per megaparsec. Total matter density parameter, including dark and ordinary matter, runs approximately 0.315. For a spatially flat universe, this implies dark energy density parameter of approximately 0.685. This means roughly 68.5% of the universe's energy density today consists of dark energy. About 26.5% consists of dark matter. Only about 5% consists of ordinary matter, the atoms making up stars, planets, and people. The equation of state parameter W describes how dark energy pressure relates to its density. For a true cosmological constant, W equals exactly -1. Observations constrain W to run very close to -1, consistent with a cosmological constant, though not definitively proving it. The cosmological constant, lambda, expressed in inverse length squared units, works out to approximately 1.1 times 10 to the -52 per square meter. This tiny number sets a characteristic length scale for the universe. Taking inverse square root of lambda gives length of approximately 9.6 times 10 to the 25 meters, about 10.1 billion light years, roughly 5.9 times 10 to the 22 miles. This scale characterizes where cosmological constant effects become dominant. Observed vacuum energy density of about 5.8 times 10 to the -27 kilograms per cubic meter translates to roughly 3 to 4 proton masses per cubic meter. An incredibly dilute energy density spread across cosmic scales, adding up to 2/3 of everything. Clarifying what observations actually tell us about dark energy matters here. Directly detecting vacuum energy lies beyond our reach. Putting vacuum in a jar and weighing it cannot be done. What we observe are effects of accelerating expansion on distant objects. Supernovae appear dimmer than expected for their redshift, meaning they sit farther away than expected, meaning space expansion between us and them runs faster than expected, meaning something accelerates the expansion. Cosmic microwave background patterns depend on universal geometry and content. A flat universe, which observations strongly support, requires total energy density equaling a critical value. Matter alone falls short. Something else must contribute. Something with properties that do not dilute as the universe expands. Large-scale structure, galaxy distribution across the cosmos, carries imprints of both matter and dark energy. Structure growth depends on how gravity pulls matter together, which depends on what else occupies the universe. Dark energy slows structure growth by pulling space apart. Baryon acoustic oscillations, sound waves from the early universe frozen into galaxy distribution, provide a standard ruler measurable at different cosmic epochs. These measurements trace expansion history and constrain dark energy properties. All observations converge on a consistent picture. Something constituting about 2/3 of universal energy behaves like a cosmological constant with equation of state parameter W close to -1. Determining from observations alone whether this truly represents a cosmological constant, constant in space and time, or some dynamical dark energy that might vary, remains impossible. Current measurements stay consistent with a constant, without ruling out mild evolution. The DESI collaboration and other next-generation surveys test this with unprecedented precision. Any deviation from W equaling -1 would constitute evidence for something beyond a simple cosmological constant. Whether dark energy turns out constant or dynamical The vacuum catastrophe remains. The question is why this component has the tiny energy density it does, not whether that density stays exactly constant. Future observations will continue probing dark energy, even if they cannot directly solve the vacuum catastrophe. The Vera C. Rubin Observatory, formerly known as LSST, will conduct an unprecedented southern sky survey beginning in the mid-2020s, discovering millions of supernovae, measuring billions of galaxies, and mapping matter distribution with exquisite precision. The Nancy Grace Roman Space Telescope, scheduled for mid-2020s launch, will study dark energy through multiple methods: supernovae, baryon acoustic oscillations, and gravitational lensing, with wide field of view and sharp resolution opening new windows on cosmic expansion. The European Space Agency's Euclid mission, launched in 2023, already collects data on galaxy shapes and distributions to constrain dark energy, combining visible and infrared observations to probe how cosmic structure grew under dark energy influence. The DESI experiment continues mapping three-dimensional galaxy distribution, measuring baryon acoustic oscillation evolution over cosmic time, providing one of the cleanest probes of cosmic expansion history. All these observations will refine knowledge of how dark energy behaves, testing whether equation of state parameter W runs exactly -1 or deviates slightly, constraining or ruling out various dynamical dark energy models. What they will not do is explain why vacuum energy runs so small. That requires theoretical breakthrough, not just better measurements. Observations tell us what nature does. Theory must explain why. Observational programs hold value regardless. Understanding dark energy behavior constrains theoretical possibilities. If observations find W deviating from -1, that points away from a simple cosmological constant toward something more complex. If W remains stubbornly at -1, the simplest explanation survives, but the vacuum catastrophe stays unexplained. Each quantum field contributes to vacuum energy, and being specific about what this means helps. The electromagnetic field, mediating light and electromagnetic interactions, has vacuum fluctuations. Every mode of the electromagnetic field, every frequency and direction, possesses a ground state with zero-point energy. The electron field, describing electrons and positrons, also carries vacuum fluctuations. The ground state is not empty, but contains particle possibilities, a background of virtual fluctuations. Quark fields, describing proton and neutron constituents, contribute their own vacuum energy. The gluon field, mediating the strong force binding quarks, contributes as well. The Higgs field stands particularly interesting. Unlike other fields, the Higgs field carries a non-zero value even in its ground state. This non-zero value gives particles their masses through the Higgs mechanism, and the energy associated with this non-zero value adds another vacuum energy contribution. Neutrino fields, describing the elusive neutrinos passing through ordinary matter almost unimpeded, add their contributions. W and Z boson fields, mediating the weak force, add more. Every standard model field contributes. Summing all contributions using a Planck scale cutoff produces the enormous theoretical prediction. Contributions from different fields carry different signs. Bosonic fields contribute positive energy. Fermionic fields contribute negative energy. In principle, these could cancel, but they do not cancel in the Standard Model. The Standard Model lacks supersymmetry. Bosons and fermions do not arrive in matched pairs. Cancellation remains incomplete. Even more complete cancellation, reducing vacuum energy by many orders of magnitude, would leave residue vastly exceeding observation. The problem is not that different contributions fail to cancel, but the scale of each contribution before any cancellation. Imagining what the universe would be like if vacuum energy approached the theoretical prediction helps convey the stakes. Vacuum energy density at Planck scale would produce enormous expansion rate. The characteristic expansion timescale would run on order of Planck time, about 10 to the negative 44 seconds. The universe would double in size roughly every 10 to the negative 44 seconds. Before any structures could form, before atoms could combine, before galaxies could coalesce, space itself would be flying apart at rates making our current cosmic expansion look frozen by comparison. No stars would form, no planets, no life. Nothing resembling the universe we observe could exist. This is why the word catastrophe applies. Not that the calculation fails some abstract elegance test, but that if the calculation were correct, we would not be here to discuss it. The universe would be radically incompatible with structure formation, with chemistry, with complexity of any kind. Our existence, the existence of galaxies, the evolution of the universe over billions of years into its current state, places an upper limit on vacuum energy density. That upper limit runs enormously smaller than what quantum field theory predicts. Something cancels the vacuum energy. Something suppresses it by a factor of 10 to the 120. Nobody knows what that something is. Even using more conservative cutoff, the problem persists. Arguing we should not trust quantum field theory up to Planck scale, placing cutoff at electroweak scale around a few hundred GeV where electromagnetic and weak forces unify, a scale we have actually probed experimentally at the Large Hadron Collider, using this cutoff still overshoots observed vacuum energy by many orders of magnitude. The mismatch runs smaller than 120 orders, but remains enormous, utterly inexplicable within current frameworks. No known energy scale makes the naive calculation give the right answer. The problem is not sensitive to cutoff placement, as long as that cutoff sits above the observed vacuum energy scale of about 10 to the negative 3 electron volts. The Friedmann equation, the fundamental equation governing cosmic expansion, relates expansion rate to universal energy density. Higher energy density means faster expansion. At Planck scale vacuum energy density, expansion rate would run on order of 1 over Planck time. The universe would double in size roughly every 10 to the negative 44 seconds. For comparison, current expansion rate, characterized by Hubble constant, runs about 67.4 kilometers per second per megaparsec, corresponding to doubling time of about 10 billion years. The ratio of 10 billion years to 10 to the negative 44 seconds runs about 10 to the 60. Planck scale expansion would be 10 to the 60 times faster than current expansion. At such expansion rates, matter could never clump together. Gravity operates slowly compared to this expansion. Any perturbation that might grow into a galaxy would be stretched apart before gravity could act. Standard cosmology has the early universe going through phases of slower expansion, during which matter could clump. First, tiny density variations grew. Then, larger structures formed hierarchically, with galaxies emerging, then clusters, then the cosmic web we observe today. This process took billions of years. Matter needed time to fall together, to merge, to build up structures. Expansion was happening simultaneously, fighting against gravity. But gravity was winning on small scales. If vacuum energy had dominated from the beginning at Planck scale, expansion would have won everywhere, always. No structures would have formed, no stars to forge heavy elements, no planets to host life, no observers to wonder about cosmology. This is not philosophical argument, but physical calculation. General relativity equations applied to Planck-scale vacuum energy predict a universe incompatible with our existence. Our existence constitutes data constraining vacuum energy to run vastly smaller than naive prediction. Whether vacuum energy is real at all might puzzle you. Perhaps the calculation runs fundamentally wrong. Perhaps zero-point energy is a mathematical artifact with no physical consequence. The Casimir Effect suggests otherwise. In 1948, Dutch physicist Hendrik Casimir predicted a strange phenomenon. Place two uncharged, perfectly conducting plates parallel to each other in vacuum, and they will attract. No electric charge, no magnetic fields, just two metal plates in empty space pulling toward each other. The reason involves vacuum fluctuations. Between the plates, only certain electromagnetic modes can exist, modes whose wavelengths fit an integer number of times between plates. Outside the plates, all modes can exist. This difference in allowed modes creates difference in vacuum energy density, lower between plates than outside. Result is net pressure pushing plates together. Casimir force depends on plate separation. Specifically, pressure scales as inverse fourth power of separation. Bring plates closer and force increases dramatically. Using the formula for ideal parallel plates, with pressure equaling pi squared times h bar times c divided by 240 times separation to the fourth power, pressure at various separations can be calculated. At separation of 1 micrometer, about 3.94 times 10 to the negative 5 inches, pressure runs approximately 0.0013 pascals. Tiny, at about 100 billionth of atmospheric pressure. At 100 nanometers separation, about 3.94 times 10 to the negative 6 inches, pressure rises to approximately 13 pascals, still small but becoming noticeable. At 10 nanometers separation, about 3.94 times 10 to the negative 7 inches, pressure jumps to approximately 1.3 times 10 to the 5 pascals, roughly 19 pounds per square inch, comparable to atmospheric pressure. Laboratory measurements of the Casimir effect, notably high-precision experiments beginning in the 1990s, confirm the theoretical predictions. Vacuum fluctuations produce real, measurable forces. This confirms that vacuum modes matter. Changes in vacuum configuration, changes in which modes are allowed, create physical effects. The vacuum is not nothing. It has structure, and that structure can be probed. Hendrik Casimir made his prediction in 1948, before quantum electrodynamics reached full development. He reasoned from first principles about how vacuum modes between conducting plates would differ from modes in unbounded space. Between two parallel plates, only electromagnetic modes whose wavelengths fit properly can exist. Plates impose boundary conditions. Modes that do not fit get excluded. Outside plates, no such restriction applies. All modes exist. Difference in mode count means difference in vacuum energy. Vacuum energy per unit volume runs lower between plates than outside. This difference creates net pressure pushing plates together. Measuring this force presents technical challenges. Plates must sit very close together for detectable force. At micrometer separations, force runs tiny. At nanometer separations, force becomes significant, but keeping surfaces parallel at such scales proves extremely difficult. In 1997, Steve Lamoureux performed high-precision Casimir force measurement using a torsion pendulum. He measured force between plate and sphere, avoiding some alignment issues, finding agreement with theory at the percent level. Subsequent experiments refined these measurements using different techniques: atomic force microscope measurements, microelectromechanical systems, and cavity optomechanics. Theoretical predictions match observations. What these experiments confirm is that changes in vacuum mode structure produce real forces. The vacuum is not passive. Its properties depend on boundary conditions, and those properties carry measurable consequences. Careful distinction matters about what Casimir effect does and does not tell us. The Casimir effect demonstrates that differences in vacuum energy between configurations are real and measurable. It does not reveal vacuum energy's absolute value. It tells us that changing boundary conditions changes vacuum energy, and that change produces force. This resembles knowing one room is warmer than another without knowing either room's absolute temperature. Temperature difference is measurable. Individual temperatures require additional information. The Casimir effect confirms vacuum energy is not pure fiction. Changes in vacuum configuration carry physical consequences. But it does not resolve the cosmological constant problem, because the problem concerns absolute value, not differences. Ordinary quantum field theory without gravity treats absolute value as irrelevant. You can shift all energies by a constant and no prediction changes. The Casimir effect involves differences, unchanged by such shifts. Gravity differs. General relativity cares about absolute energy density, not just differences. Vacuum energy, whatever its value, curves space-time. Here is where the problem becomes acute. Some physicists have argued perhaps gravity does not couple to vacuum energy the way we assume. That perhaps something special about vacuum energy makes it gravitationally inert. No consistent theory implementing this idea has been constructed, though. General relativity treats all energy democratically. No known mechanism singles out vacuum energy for special treatment. The Casimir effect reminds us vacuum has physical properties, is not empty in any straightforward sense. Boundary conditions matter. Mode counting matters. The vacuum carries rich structure. But that structure, when you attempt calculating total energy density and ask how gravity responds, leads to catastrophe. Physicists have proposed many possible solutions to the vacuum catastrophe. None has achieved consensus. The main approaches and why each faces difficulties deserve examination. The first approach invokes symmetry, proposing some symmetry cancels vacuum energy. Supersymmetry is the most studied candidate. Supersymmetry proposes every particle has a partner particle with different spin properties. Bosons have fermionic partners. Fermions have bosonic partners. Zero-point energies of bosons and fermions carry opposite signs, so exact supersymmetry would cancel them perfectly. The problem is, supersymmetry is not exact in our universe. We observe no partner particles at same masses as ordinary particles. If supersymmetry exists, it must be broken at some energy scale. And broken supersymmetry does not cancel vacuum energy, but leaves residue proportional to the symmetry breaking scale, which itself runs much larger than observed cosmological constant. Supersymmetry might reduce the problem from 120 orders of magnitude to perhaps 60, depending on where breaking occurs. This constitutes progress of a sort, but 60 orders of magnitude still represents astronomical discrepancy. Supersymmetry existence in nature must involve breaking at some energy scale. Superpartners must be heavier than ordinary counterparts, heavy enough to have escaped detection so far. Current Large Hadron Collider limits push most superpartner masses above several hundred GeV or even a TeV. Broken supersymmetry does not give zero vacuum energy, but vacuum energy proportional to supersymmetry breaking scale to the fourth power. Breaking at a TeV gives vacuum energy of order TeV to the fourth, far larger than observed. Supersymmetry can reduce the vacuum catastrophe, but not eliminate it, potentially turning 120 orders of magnitude into 60, depending on breaking scale. Progress, but 60 orders of magnitude still constitutes cosmic gulf between prediction and observation. No superpartner has been discovered, despite extensive searches. Large Hadron Collider searches have found nothing. Supersymmetry might not exist in nature at all, or might be broken at scales too high to help much with vacuum energy. The second approach involves dynamical mechanisms, proposing vacuum energy is not constant, but adjusts itself over time, relaxing to small value through some dynamical process. Various models propose fields evolving to cancel vacuum energy, or mechanisms screening vacuum energy from gravitational effects. These models exist mathematically, but face theoretical challenges, particularly explaining why adjustment is so precise and why it leaves the tiny residual value we observe. The third approach involves modified gravity, proposing general relativity is wrong at cosmological scales, and the true gravity theory does not respond to vacuum energy the same way. General relativity has been extraordinarily well tested. The 1919 solar eclipse observed starlight bending by the sun, confirming Einstein's prediction. Mercury's orbital precession, unexplained by Newtonian gravity, finds precise explanation through general relativity. Gravitational waves from merging black holes, detected by LIGO in 2015, match general relativity predictions to exquisite precision. Any general relativity modification must reproduce all these successes. It must agree with general relativity in all tested regimes, including solar system scales, binary pulsar orbits, and gravitational wave observations. The modification would need to be specific to vacuum energy, with gravity responding normally to ordinary matter and radiation, but not responding, or responding differently, to vacuum energy. Constructing such a theory proves difficult. General relativity is remarkably rigid, its structure tightly constrained by mathematical consistency requirements. Simply adding a switch turning off gravity's response to certain energy kinds cannot be done. Various proposals exist. Degravitation models suggest vacuum energy might lose gravitational effect over cosmic timescales. Massive gravity theories give the graviton mass, changing how gravity behaves at large distances. Extra-dimensional theories allow vacuum energy to leak into other dimensions. None of these proposals has achieved consensus. Each faces theoretical challenges, and none naturally explains why effective cosmological constant has the tiny value we observe. The problem is, any successful modification must be extremely fine-tuned, cancelling or neutralizing vacuum energy to 120 decimal places while leaving all other gravitational physics intact. This fine-tuning is just as puzzling as the original problem. Modified gravity remains an active research area. Future observations of cosmic expansion, gravitational waves, and large-scale structure might constrain or support various modifications. But no compelling solution has emerged. The fourth approach runs more controversial: anthropic selection within a landscape of possibilities. The idea starts with observing that if cosmological constant ran much larger than observed, galaxies could not form, stars could not shine long enough for complex chemistry to develop, and observers could not exist to ask the question. If many different universal regions exist, or many different universes, with different cosmological constant values, observers will only find themselves in regions where the constant runs small enough to permit their existence. We would observe small cosmological constant not because physics requires it, but because we could not exist to observe anything else. This anthropic reasoning has adherents, particularly among physicists taking the string theory landscape seriously. String theory appears to allow enormous numbers of different vacuum configurations, perhaps 10 to the 500 or more, each with different physical parameters. If all configurations are realized somewhere, anthropic selection might explain why we see particular values. Critics object. This approach abandons explanation in traditional sense. It does not reveal why cosmological constant has its particular value, but tells you that among all possible values, only certain ones are compatible with observers. This feels to many like avoiding the question rather than answering it. Debate between those embracing anthropic reasoning and those rejecting it reflects deeper disagreements about what counts as scientific explanation. Both camps include serious physicists. Neither possesses a decisive argument against the other. What everyone agrees on is no approach has solved the problem. The vacuum catastrophe remains unsolved, persisting through decades of effort by brilliant physicists, connecting the smallest physics scales where quantum fluctuations occur to the largest scales where the cosmos expands, resisting resolution. I find this aspect of the problem both frustrating and fascinating. Physics can predict electron magnetic moment to 12 decimal places. It can calculate early universe nuclear reaction yields with remarkable accuracy. The same physical principles applied to vacuum energy produce an answer missing observation by a factor larger than any other discrepancy in science history. Stephen Weinberg's 1989 review of the cosmological constant problem remains a touchstone for the field. Weinberg, a Nobel laureate who made fundamental standard model contributions, systematically analyzed every proposed solution and found none fully satisfactory. He categorized approaches as symmetry-based, dynamical, and anthropic. Symmetry-based approaches sought principles forcing cosmological constant to zero. Dynamical approaches sought mechanisms driving it to zero over time. Anthropic approaches argued observers could only exist in regions where it was small. For symmetry-based approaches, Weinberg noted no known symmetry of nature sets cosmological constant to zero. Supersymmetry helps, but does not solve the problem when broken. Other proposed symmetries either do not actually force zero vacuum energy or have other problems. For dynamical approaches, Weinberg examined models where fields evolve to cancel vacuum energy, facing the challenge of explaining why cancellation is so precise and why it leaves the particular small observed value. For anthropic approaches, Weinberg made a remarkable prediction. If anthropic reasoning were correct, cosmological constant should not be exactly zero, but should have a small positive value, roughly the largest value compatible with galaxy formation. A decade later, observations confirmed a small positive cosmological constant in roughly the predicted range. This predictive success has led some physicists to take anthropic reasoning more seriously. Accepting that many different vacuum configurations exist, perhaps in different regions of a vast multiverse, we would expect finding ourselves in a region where cosmological constant is small enough for galaxies, but not necessarily zero. Critics argue this is not really explanation, not revealing why cosmological constant has its value, but telling you that among all possible values, only certain ones allow observers. This feels like giving up on fundamental explanation. Weinberg himself was cautious about anthropic reasoning, presenting it as one possibility among several without definitive endorsement. The vacuum catastrophe sometimes receives framing as a naturalness problem. In physics, naturalness refers to the expectation that dimensionless ratios should be of order unity, or at least not enormously different from unity. When a parameter runs tiny compared to expectation, something must be suppressing it, and finding that something often proves productive. Electron mass runs about 0.5 MeV, while Planck mass runs about 10 to the 19 GeV, a ratio of about 10 to the negative 22. This seems unnatural. Why is the electron so much lighter than Planck scale? Various mechanisms can explain such hierarchies. electron mass is protected by a symmetry, chiral symmetry, which would make it exactly zero if unbroken. Small but non-zero mass arises from symmetry breaking at low scale. The naturalness problem is solved, or at least addressed. The cosmological constant seems far more unnatural. Observed value runs about 10 to the negative 120 times what naive dimensional analysis suggests. No known symmetry protects such small value. No mechanism dynamically drives it to this value. Some physicists argue naturalness expectations might be wrong, that perhaps the universe is not required to satisfy our aesthetic preferences, that perhaps parameters can be fine-tuned without explanation. This response troubles many physicists. Naturalness has historically been a good guide. When parameters seemed unnatural, there was usually a reason. Abandoning naturalness feels like abandoning explanatory power. Others argue the vacuum catastrophe shows naturalness limits as a principle, that perhaps in quantum gravity the concepts we use to frame the problem do not apply as assumed, that perhaps the naive calculation is simply not the right calculation. The debate reflects deeper uncertainty about doing physics in regimes we cannot directly probe. Planck's scale sits far beyond experimental reach. We have theories and consistency arguments, but not data. In such situations, principles like naturalness guide reasoning, but the principles themselves remain uncertain. Current observations continue refining dark energy understanding while leaving the theoretical puzzle untouched. The DESI collaboration, operating the Dark Energy Spectroscopic Instrument, has released large-scale structure analyses. These observations use baryon acoustic oscillations, imprints of early universe sound waves frozen into galaxy distribution, measuring cosmic distances and expansion history. DESI data, combined with other observations, continues testing whether equation of state parameter, W, runs exactly -1, as true cosmological constant requires, or varies with time, suggesting dynamical dark energy. Current constraints stay consistent with W equaling -1 to good accuracy. If deviations exist, they run small. Dark energy behaves very much like a cosmological constant. This matters because dynamical dark energy, where W changes over time, would suggest different physics from true cosmological constant. But even if dark energy turns out dynamical rather than constant, this would not by itself explain the vacuum catastrophe. The puzzle is why vacuum energy runs so small, regardless of whether that small value is constant or varies slightly. The cosmological constant problem is a theory-observation naturalness gap, not just a measurement issue. Better measurements help constrain what dark energy is doing, but do not explain why quantum field theory's prediction runs so wildly wrong. The problem lies at the intersection of quantum mechanics and gravity, signaling something fundamental is missing from our understanding. Either quantum field theory is wrong in how it calculates vacuum energy, or general relativity is wrong in how gravity couples to vacuum energy, or some new physics intervenes in ways we do not yet understand. More precise measurements will not solve this problem directly. It requires theoretical breakthrough. Some physicists believe breakthrough will come from quantum gravity. String theory, loop quantum gravity, and other approaches to unifying quantum mechanics with general relativity might reveal how vacuum energy actually behaves when both frameworks are properly combined. Others are less optimistic, noting decades of effort in these directions have not produced a solution. The cosmological coincidence problem adds another mystery layer to the vacuum catastrophe. Dark energy density and matter density run comparable today. Matter makes up about 31.5% of the universe's energy budget. Dark energy makes up about 68.5%. These are the same order of magnitude, but they evolve differently over cosmic history. Matter density decreases as the universe expands. Spread same mass over more volume and density drops. As the universe doubles in size, matter density drops by a factor of 8 because volume increases as lengths cube. Dark energy density, if truly a cosmological constant, does not decrease. It is a property of space itself, the same in every cubic meter regardless of how many cubic meters exist. As the universe expands, dark energy density stays constant while matter density drops. In the early universe, matter density vastly exceeded dark energy density. Dark energy was negligible. The universe was matter-dominated, and gravity pulled structures together. In the far future, dark energy will completely dominate. Matter density will become negligible. The universe will be dark energy dominated, expanding ever faster, with no new structures forming. Today, we happen to live at the transition, at the cosmic epoch when matter and dark energy run comparable. This transition happens once in universal history. Why are we here to observe it? One response is anthropic. The transition epoch is also when complex structures like galaxies, stars, and observers can exist. Before the transition, structure was still forming. After the transition, existing structures will be isolated and decay. The observer window is narrow, and we are in it. Another response is that this is just coincidence, not requiring explanation. The universe is the age it is. We are here when we are. Nothing more to say. A third response proposes dark energy is not cosmological constant, but something dynamical, tracking matter density to some degree. Various quintessence models propose scalar fields evolving in ways keeping dark energy comparable to matter. These models face their own challenges, but at least address the coincidence. The coincidence problem is distinct from the vacuum catastrophe, but related. Both involve dark energy having properties that seem special or fine-tuned. Both lack satisfying explanations. What would a solution to the vacuum catastrophe look like? What would count as resolving this problem? One possibility is a mechanism cancelling vacuum energy's gravitational effect specifically. Perhaps vacuum energy exists and runs large, but something prevents it from curving space-time. This would require modifying either quantum field theory or general relativity in ways not yet achieved. Another possibility is that the naive calculation is simply wrong, that a correct way to calculate vacuum energy exists, giving small answer. Perhaps summing over modes is not the right procedure. Or perhaps regularization and renormalization in gravity's presence work differently than assumed. This would require understanding quantum field theory in curved spacetime better than we currently do. A third possibility is quantum gravity changes the picture entirely. Perhaps in the correct theory unifying quantum mechanics and gravity, the concepts we use discussing vacuum energy do not apply the same way. The naive estimate might be comparing wrong quantities. What probably would not count as solution is simply accepting the small value as input. Saying cosmological constant is small because that is what we observe, without explaining why, would leave the puzzle untouched. The problem is the mismatch between calculation based on well-established physics and observation, not just smallness itself. The vacuum catastrophe suggests we are missing something basic about how quantum fields and gravity interact. It is signpost, pointing toward new physics, even if we cannot yet read where it points. I remember the first time I truly grasped this problem's scale. I had read about the 120 orders of magnitude mismatch, but the number was abstract, just digits on a page. Not until I tried constructing an analogy, finding something to compare 10 to the 122, did the enormity land. Nothing in ordinary experience gives intuition for such a number. It runs beyond astronomical. It runs beyond anything. Yet it emerges from straightforward application of physics we trust in other contexts. The connection between laboratory physics and cosmic physics stands as one of this problem's most remarkable aspects. In a laboratory, you can set up two metal plates a micrometer apart and measure tiny force between them. This is the Casimir Effect, direct consequence of vacuum fluctuations, of zero-point energy quantum mechanics demands. In the cosmos, you can observe distant supernovae, map cosmic microwave background, trace galaxy distribution across billions of light years. These observations reveal the universe is accelerating in expansion, driven by something acting like a cosmological constant. The same equations connect both phenomena. Vacuum energy producing Casimir force should gravitate. Zero-point oscillations of quantum fields should curve space-time. Laboratory physics and cosmic physics meet in the cosmological constant. At that meeting point, numbers disagree by 120 orders of magnitude. This is not abstract theoretical puzzle confined to blackboards and academic journals. Real measurements exist at both ends. The Casimir force has been measured. Cosmic acceleration has been measured. Both measurements are solid. The theoretical framework connecting them, quantum field theory plus general relativity, is the best physics we have. It works everywhere else we have tested it. Here, it fails catastrophically. Understanding why it fails would illuminate both quantum and cosmic. It would reveal something about vacuum fluctuations, something about gravity, something about how smallest and largest scales connect. The vacuum catastrophe is not just problem to be solved, but window into deeper physics. Observed dark energy density of about 5.8 times 10 to the negative 27 kilograms per cubic meter deserves more context. In energy terms, this runs about 5.2 times 10 to the negative 10 joules per cubic meter, about 3.3 kiloelectron volts per cubic centimeter. Feeling what 3.3 keV means? visible light photon has energy of about 2 electron volts. So, X-ray photon has energy of thousands of electron volts. A kilo electron volt equals 1,000 electron volts in the soft X-ray range. So, vacuum energy density per cubic centimeter equals about 3 soft X-ray photons worth of energy, extraordinarily small by any particle physics standard. Comparing to other energy densities you might encounter helps. Sunlight energy density at Earth's surface runs about 0.001 joules per cubic meter, millions of times larger than dark energy density. Energy density inside a nuclear reactor might run millions of joules per cubic meter, quadrillions of times larger than dark energy. Energy density at nuclear explosion center reaches values dwarfing anything in everyday experience. Still, nothing compared to what quantum field theory predicts for vacuum. If vacuum energy ran at Planck scale, would be about 10 to the 113 joules per cubic meter. Energy in 1 cubic centimeter of Planck scale vacuum would exceed total solar energy output over its entire lifetime. Clearly, that is not what we observe. Empty space is not exploding with energy. The vacuum appears, to all observations, nearly empty. Yet quantum field theory says those vacuum modes are there, those fluctuations are happening, that zero-point energy is present. The Casimir Effect confirms vacuum modes exist and have effects. Something must be suppressing their gravitational influence by incomprehensible factor. The vacuum catastrophe points directly toward the need for quantum gravity. We have quantum mechanics describing particle and field behavior at small scales. We have general relativity describing gravity and space-time at large scales. Each theory works extraordinarily well in its domain. When we try combining them, problems appear. The vacuum catastrophe is one of the most severe. Quantum field theory calculates vacuum energy. General relativity says that energy should curve space-time. The combination produces absurd results. This suggests naive combination is wrong. Either quantum field theory works differently in gravity's presence than we assume, or gravity responds to quantum effects differently than general relativity predicts, or both theories must be replaced by something deeper at their intersection. Let me revisit the key numbers to ensure they are clear. Observed dark energy density runs approximately 5.8 times 10 to the negative 27 kilograms per cubic meter, corresponding to about 3.7 times 10 to the negative 28 pounds per cubic foot. In energy terms, roughly 5.2 times 10 to the negative 10 joules per cubic meter, about 3.3 kiloelectron volts per cubic centimeter. This is extraordinarily dilute. A cubic meter of air at sea level contains about 1.2 kilograms. Dark energy equivalent mass in that same cubic meter amounts to a few proton masses, about 26 orders of magnitude less than air. Yet this dilute energy, spread across space's vastness, constitutes about 68.5% of the universe's total energy budget today. Dilute per cubic meter, but dominant when summed across the cosmos. The theoretical prediction using Planck scale cutoff gives vacuum energy density of order Planck energy to the fourth power, working out to roughly 10 to the 113 joules per cubic meter, depending on exactly how calculation proceeds. Comparing 10 to the 113 to 10 to the negative 10 gives ratio of 10 to the 123, or thereabouts. This is where the 120 orders of magnitude figure originates, with some variation, depending on exactly how quantities are defined and calculated. Even using much lower cutoff, say electroweak scale of a few hundred GeV, rather than Planck scale of 10 to the 19 GeV, prediction still vastly overshoots observation. Electroweak vacuum energy would run order of a few hundred GeV to the fourth power, still many orders of magnitude above what is observed. No safe harbor exists. No cutoff choice makes calculation agree with observation, unless choosing a cutoff at the ridiculously low scale of about 10 to the negative 3 electron volts, far below any energy where physics actually changes character. The problem is robust, not depending on fine calculation details, but emerging from basic quantum field theory and general relativity principles. Think about what this means before we proceed. The same quantum field theory, predicting electron behavior in atoms, underlying the transistors in your phone, enabling atomic clock precision, predicts vacuum energy 120 orders of magnitude larger than what we observe. Either that prediction runs wrong in ways we do not understand, or something cancels it to 120 decimal places, or we are missing something fundamental about how the universe works. What would you guess is happening? Before I tell you what physicists think, take a moment to consider possibilities. If the calculation is simply wrong, we need to identify what went wrong. Mathematics follows from standard principles. Checking and rechecking over decades has not found an error. The calculation might be naive or incomplete, but calling it wrong requires showing what went wrong. If something cancels vacuum energy, that cancellation must be extraordinarily precise. Cancelling 120 orders of magnitude requires mechanism working to 120 decimal places. No known symmetry achieves this. Supersymmetry might help, but does not fully solve the problem. If we are missing something fundamental, that something must somehow evade detection in all other contexts. Quantum field theory works extraordinarily well for everything except this. Whatever is missing must leave all other predictions intact while dramatically changing this one. None of these options sits comfortably. Each requires accepting something surprising or unexplained. This is the position physics finds itself in, a problem resisting solution for over half a century, a discrepancy larger than any other in science history, a puzzle connecting the deepest questions about quantum mechanics and gravity. When I first learned about this, I had to put down the book and just sit with it. The mismatch scale was difficult to absorb. We are not talking about small correction needing adjustment, but a prediction missing by a factor containing 120 zeros. The interconnection between these research threads reveals consistent picture. Laboratory measurements confirm vacuum fluctuations exist and produce real forces. Cosmological observations confirm accelerating expansion driven by something like a cosmological constant. Theoretical physics connects these through equations that work everywhere else we have tested them. At the interface, where laboratory physics meets cosmological physics, the equations disagree by incomprehensible margin. This disagreement is not an artifact of sloppy calculation or uncertain measurement. Both ends are solid. The disagreement is real. This convergence makes the vacuum catastrophe unique among physics problems. Multiple independent approaches using different methods and addressing different questions arrive at the same puzzle. When independent approaches agree that something is wrong, something usually is. The situation resembles earlier physics, moments before major breakthroughs. Before quantum mechanics unified wave and particle pictures of light, multiple evidence lines pointed towards something strange about photon behavior. Before general relativity unified gravity and geometry, multiple puzzles suggested Newtonian gravity was incomplete. We may be at a similar moment regarding vacuum energy. The puzzles are accumulating, the hints are becoming clearer. A unified understanding may be approaching, though what form it will take remains uncertain. What makes this moment special is convergence of theoretical tools. We have holography from string theory, amplitude methods from particle physics, quantum information from computer science, and precision cosmology from observational astronomy. These fields are cross-pollinating, generating new ideas neither could have produced alone. The next decade may bring breakthroughs we cannot anticipate, or it may reveal the puzzles are even deeper than currently imagined. Either outcome would advance understanding. The Lambda CDM model deserves fuller description because it represents our best current cosmic model. Lambda refers to cosmological constant, Einstein's symbol for vacuum energy term in his equations. CDM stands for cold dark matter, invisible matter comping gravitationally but not interacting electromagnetically. Together with ordinary baryonic matter, atoms making up stars, planets, and people, these components describe universal energy content. According to Planck 2018 results, current energy budget breaks down as follows. Dark energy, the lambda component, contributes approximately 68.5%. Dark matter contributes approximately 26.5%. Ordinary matter contributes approximately 5%. We are a tiny minority. Atoms in your body, in Earth, in the Sun, in every visible star, constitute only about 1/20th of universal energy budget. The rest is dark matter, detected only through gravity, and dark energy, detected only through cosmic expansion effects. The Lambda CDM model fits observations remarkably well. Cosmic microwave background, galaxy distribution, light element abundances from early universe nucleosynthesis, oldest star ages, all stay consistent with this model. What the model does not explain is why parameters have their values. Why is dark energy 68.5%? Why is dark matter 26.5%? The model takes these as inputs from observation, not predictions from theory. The cosmological constant problem asks specifically about lambda component. Given what we know about quantum field theory, lambda should run enormous. Observation says it runs tiny. The model accommodates this by using observed value. But that is not explanation. A complete theory would derive lambda value from more fundamental principles. No such theory exists. Type 1a supernovae deserve more attention because they enabled the accelerating expansion discovery. Type 1a supernovae are white dwarf star explosions that have accumulated too much matter from a companion. When white dwarf exceeds critical mass, the Chandrasekhar limit of about 1.4 solar masses, runaway nuclear fusion occurs and it explodes. These explosions have remarkably consistent peak brightness. Explosion physics is determined by mass threshold, which stays always the same. This makes Type 1a supernovae standard candles, objects whose intrinsic brightness is known. Measure apparent brightness and you can calculate distance. Two teams independently used Type 1a supernovae to measure universal expansion history. The Supernova Cosmology project, led by Saul Perlmutter, and High Z Supernova Search Team, led by Brian Schmidt with Adam Rees as key member, both observed distant supernovae expecting expansion deceleration. The expectation was deceleration. Matter attracts matter through gravity. A universe filled with matter should have expansion slowed by mutual gravitational attraction. More matter means more deceleration. What both teams found was opposite. Distant supernovae appeared dimmer than expected, meaning they sat farther away than expected, meaning expansion had not slowed as expected. It had sped up. This shocked the field. No mainstream cosmological model at the time predicted accelerating expansion. The cosmological constant had been largely ignored, assumed zero. Suddenly, it was not only non-zero, but dominant. Initial skepticism met the result. Systematic errors were scrutinized, alternative explanations were proposed. Perhaps dust was dimming supernovae. Perhaps Type 1a supernovae in distant past were intrinsically different. Over following years, independent evidence accumulated. Cosmic microwave background showed patterns consistent with flat universe, requiring dark energy to balance observable matter. Large-scale structure surveys showed clustering patterns consistent with dark energy. Every observation pointed the same direction. Accelerating expansion is now established cosmological fact. Its cause remains mysterious. The vacuum catastrophe tells us something important about current physics state. Quantum field theory and general relativity stand as our two most successful theories. Quantum field theory describes strong, weak, and electromagnetic forces with astonishing precision. General relativity describes gravity, predicts gravitational waves, explains black holes, and underlies our cosmic expansion understanding. Each theory has been tested and confirmed in ways establishing them as reliable nature descriptions within their domains. Yet, trying to combine them, asking what quantum field theory implies for gravity, produces the vacuum catastrophe. The theories do not mesh the way they should if we had complete understanding. This constitutes strong evidence something is missing from our picture. Not that quantum field theory is wrong, Not that general relativity is wrong, but that how they connect, how quantum effects influence gravity and vice versa, is not fully understood. The quest for quantum gravity, a theory unifying quantum mechanics and general relativity, is partly motivated by problems like this. A complete quantum gravity theory might resolve the vacuum catastrophe by showing how vacuum energy actually couples to space-time curvature. String theory claims to be such a theory, but has not produced widely accepted cosmological constant solution. Loop quantum gravity makes different claims, also without resolving this issue definitively. The vacuum catastrophe serves as benchmark. Any candidate quantum gravity theory should explain why cosmological constant is what it is. Until a theory passes this test, quantum mechanics and gravity unification remains incomplete. This makes the vacuum catastrophe more than academic curiosity. It is signpost, marking understanding's edge, pointing toward territory not yet mapped. Speculating about what solution to the vacuum catastrophe might look like helps frame the problem. A satisfying solution would not just produce the right number, but explain why the number is what it is. It would make cosmological constant smallness seem natural rather than fine-tuned. One possibility has a new symmetry existing, not supersymmetry, but something else, forcing vacuum energy to run small or zero. This symmetry would have to be broken in ways leaving tiny residue. Observed cosmological constant would be residue of almost complete cancellation enforced by symmetry. Finding such symmetry would constitute major breakthrough, likely revealing new particles or forces testable in principle, even if far beyond current technology. The symmetry would constrain other physics aspects, making predictions that could be checked. Another possibility has gravity itself being different at cosmic scales. Perhaps general relativity, while correct at solar system and binary pulsar scales, fails at cosmological scales, in ways decoupling vacuum energy from space-time curvature. This would require modifying Einstein's equations while preserving their successes. Constructing such modifications proves difficult. General relativity is tightly constrained by mathematical consistency. Random modifications lead to inconsistencies, like ghosts, fields with negative kinetic energy making theory unstable. A successful modification would need to thread a narrow needle. A third possibility has the naive calculation simply being wrong, summing zero-point energies with cutoff not being the right procedure for determining vacuum energy in gravitational context. Perhaps in quantum gravity, vacuum energy works differently than we assume. Perhaps the question we are asking does not make sense in the correct framework. This is hard to evaluate because we lack complete quantum gravity theory. String theory and loop quantum gravity offer partial frameworks, but neither has produced clear cosmological constant answer. Resolution might also arrive from unexpected directions. Physics history contains surprises where problem solutions came from seemingly unrelated areas. The same might happen here. Reflecting on what we have covered helps consolidate understanding. We began with a number that no one can explain, 10 to the 120, representing the factor by which theoretical vacuum energy prediction overshoots observation. This stands as the largest discrepancy between theory and observation in all of science. We explored what vacuum means in physics, discovering it is far from empty. Quantum mechanics demands that even the lowest energy state of any system retains energy. This zero-point energy populates every mode of every field, filling all of space. We traced how this energy should gravitate according to general relativity, curving space-time and affecting cosmic expansion. We learned how Einstein introduced and then abandoned the cosmological constant, only for observations decades later to resurrect it. We walked through the supernova observations of 1998 that revealed accelerating expansion, and the precision cosmology that followed, pinning down dark energy to about 68.5% of universal energy budget. We confronted the catastrophe. Summing vacuum energies with any reasonable cutoff produces prediction vastly exceeding observation. No known physics explains this suppression. We examined proposed solutions, including supersymmetry, dynamical mechanisms, modified gravity, and anthropic selection, finding none fully satisfactory. And we considered what this tells us about physics' state. That our two most successful theories, when combined, produce absurd results, pointing towards something fundamental we do not yet understand. The vacuum catastrophe remains one of the deepest unsolved problems in physics. Its resolution would mark major advance. Until that resolution comes, we live with the puzzle, with the knowledge that empty space holds mysteries we cannot yet explain. Feeling what 10 to the 120 means requires creative approaches. If you had 10 to the 120 grains of sand, each 1 millimeter across, the pile would extend far beyond the observable universe by enormous margin. Roughly 10 to the 80 atoms populate the observable universe, requiring 10 to the 40 observable universes filled with atoms to reach 10 to the 120 objects. Counting one number per second, reaching 10 to the 120 would take 10 to the 120 seconds. The universe measures about 4 times 10 to the 17 seconds old, requiring roughly 10 to the 102 universe ages to finish counting. If 10 to the 120 represented dollars and the entire global economy, roughly 10 to the $14 per year devoted itself to spending them, the task would take 10 to the 106 years, about 10 to the 96 times, universal age. No quantity in any other science field involves numbers remotely this large, or mismatches remotely this severe. The gravitational constant carries precision to about 1 part in 10 to the 5. Fine structure constant carries precision to about 1 part in 10 to the 10. Electron magnetic moment agrees with calculation to about 1 part in 10 to the 12. These represent physics precision achievements. The vacuum catastrophe constitutes imprecision of 1 part in 10 to the 120. It dwarfs every other discrepancy. This is not rounding error or small overlooked correction, but failure of prediction so complete it challenges foundations of combining quantum mechanics and gravity. Let me share one more personal reflection on this problem. The vacuum catastrophe is humbling in ways few physics problems achieve. Most problems have solutions, or at least clear paths towards solutions. You can see how more work might resolve them. The vacuum catastrophe feels different. Brilliant physicists have worked on this for decades. Nobel laureates have written papers on it. Entire careers have been devoted to it. We remain, essentially, no closer to solution than in the 1980s. This is not for lack of trying. Approaches are creative and varied. Symmetries, dynamics, gravity modifications, anthropic selection, quantum gravity frameworks. Each has been explored in depth. None has worked. There is possibility the problem is simply hard, that its solution requires ideas or mathematics not yet developed. Some physics problems have persisted for centuries before finding resolution. Heat's nature remained mysterious until statistical mechanics emerged. Atomic stability remained unexplained until quantum mechanics. Perhaps the vacuum catastrophe awaits its own conceptual revolution. There is also possibility we are asking the wrong question, that the naive vacuum energy calculation is simply not the right thing to do in a theory, including gravity, that in the correct framework the question dissolves rather than being answered. We would recognize we were comparing quantities that should not be compared. And there is possibility, uncomfortable to contemplate, that some questions exceed human ability to answer. We are finite creatures with finite brains. No guarantee exists that we can understand everything about the universe. The vacuum catastrophe might mark a limit. I do not know which possibility is correct. Nobody does. That uncertainty is itself part of what makes this problem so fascinating. The vacuum catastrophe matters because it tells us something important about physics state. We have two theoretical frameworks, quantum field theory and general relativity, each extraordinarily successful in its domain. Quantum field theory describes strong, weak, and electromagnetic forces with precision reaching parts per trillion. General relativity predicts gravitational phenomena from Mercury's precession to gravitational waves from colliding black holes. Combining these frameworks in the most straightforward way, applying quantum field theory's vacuum energy prediction to general relativity's description of how energy curves spacetime, produces disastrously wrong result. This is not small discrepancy suggesting minor adjustments. It is catastrophic failure, suggesting something fundamental is missing. The vacuum catastrophe is signpost pointing toward need for deeper theory, one correctly describing how quantum effects and gravity interact. Whatever that theory turns out to be, it must resolve this problem. In the meantime, the vacuum catastrophe serves as benchmark. Proposed solutions to other problems, unified field theories, quantum gravity candidates, standard model extensions, should be checked against it. Does the proposal help with vacuum catastrophe? If not, the proposal is incomplete. This makes the vacuum catastrophe one of physics' most important unsolved problems. Its resolution would mark fundamental advance in understanding. The problem connects the smallest theorizable scales, Planck scale, to the largest observable scales, cosmological scale. It bridges particle physics and cosmology. It touches quantum mechanics and general relativity foundations. Whoever solves it will reshape physics. The solution might come from ideas already being explored, or from something nobody has yet imagined. Either way, the problem stands as challenge and opportunity. String theory attempts to provide this deeper framework. In string theory, particles are not points, but tiny vibrating strings. The theory naturally includes gravity and can, in principle, describe quantum gravitational effects. String theory famously allows enormous numbers of possible vacuum configurations, the string landscape. Different vacua have different physical parameters, including different cosmological constant values. Some researchers argue the landscape explains vacuum catastrophe through anthropic selection. Others find this unsatisfying. Loop quantum gravity takes a different approach, quantizing space-time geometry directly. Space becomes granular at Planck scale, made of discrete chunks rather than continuous fabric. This framework has its own vacuum energy perspective, though it has not produced widely accepted cosmological constant solution. Other approaches exist: causal set theory, asymptotically safe gravity, non-commutative geometry. Each offers different tools and perspectives. None has solved the vacuum catastrophe. This problem's persistence across diverse approaches suggests its difficulty. Whatever the solution, it is not obvious from any current framework. The cosmological constant history tells a story of reversals. Einstein introduced lambda in 1917 to obtain a static universe. He later abandoned it after observations revealed expansion. The cosmological constant was then largely ignored for decades, considered at best unnecessary and at worst theoretical embarrassment. In the 1960s and 1970s, quantum field theorists recognized vacuum energy should act like cosmological constant. This created a puzzle. Why is it so small, possibly zero? Most physicists assumed it equaled exactly zero. Some unknown symmetry or mechanism must be cancelling it precisely. The task was finding that mechanism. The 1998 supernova observations overturned this assumption. The cosmological constant was not zero. It carried a small positive value dominating the universe today. Einstein's discarded term had returned from the dead. This reversal made the problem harder, not easier. Explaining why something equals exactly zero might be easier than explaining why it has some particular, tiny, non-zero value. Zero might be protected by symmetry. A specific, small value appears arbitrary. The current situation has us measuring cosmological constant to reasonable precision, having theoretical reasons to expect it should run vastly larger, and having no explanation for why it is what it is. This is an uncomfortable physics position. We are accustomed to making predictions and having them confirmed, to explaining patterns and finding underlying order. Here we have prediction failing catastrophically with no clear path to understanding why. Some physicists view this as evidence we are approaching limits of what current theories can explain. Others view it as a treasure map pointing toward new physics that will revolutionize understanding. The disagreement reflects genuine uncertainty about how physics progresses from here. Stepping back to consider what all this means from a human perspective reveals something striking. We inhabit a universe whose dominant component is something we do not understand. Roughly 2/3 of all cosmic energy consists of dark energy, this mysterious something driving acceleration. We know its effects, we can measure its strength. We cannot explain why it has the value it does. Equations describing particle interactions, equations tested to extraordinary precision in laboratories, predict empty space should teem with energy. That energy should curve space-time dramatically, should dominate the cosmos from earliest moments. Somehow, that does not happen. The vast majority of predicted vacuum energy is absent, or cancelled, or hidden by some mechanism we cannot identify. This is not a minor puzzle. It touches physics foundations. It connects quantum mechanics describing the small to general relativity describing the large and gravitational. And it says these two frameworks, both spectacularly successful in their domains, do not combine the way we naively expected. Human beings living on a small planet orbiting an ordinary star in an unremarkable galaxy have developed mathematics and experiments capable of detecting this discrepancy. We measure supernovae billions of light years away. We map radiation from when the universe was young. We calculate quantum fluctuations at scales trillions of times smaller than an atom. When we put these measurements and calculations together, we find numbers do not match. The universe is not behaving the way our best theories predict. This is both humbling and exciting. Humbling because it shows understanding limits. Exciting because such mismatches have historically led to physics revolutions. When observation contradicts prediction, new physics often follows. The vacuum catastrophe tells us something important about current physics state. Quantum field theory and general relativity stand as our two most successful theories. Quantum field theory describes strong, weak, and electromagnetic forces with astonishing precision. General relativity describes gravity, predicts gravitational waves, explains black holes, and underlies cosmic expansion understanding. Each theory has been tested and confirmed in ways establishing them as reliable nature descriptions within their domains. Yet trying to combine them, asking what quantum field theory implies for gravity, produces the vacuum catastrophe. The theories do not mesh the way they should if we had complete understanding. This constitutes strong evidence something is missing from our picture. Not that quantum field theory is wrong, not that general relativity is wrong, but that how they connect, how quantum effects influence gravity and vice versa, is not fully understood. The quest for quantum gravity, a theory unifying quantum mechanics and general relativity, is partly motivated by problems like this. A complete quantum gravity theory might resolve the vacuum catastrophe by showing how vacuum energy actually couples to space-time curvature. String theory claims to be such a theory, but has not produced a widely accepted cosmological constant solution. Loop quantum gravity makes different claims, also without resolving this issue definitively. The vacuum catastrophe serves as benchmark. Any candidate quantum gravity theory should explain why. Cosmological constant is what it is. Until a theory passes this test, quantum mechanics and gravity unification remains incomplete. This makes the vacuum catastrophe more than academic curiosity. It is signpost marking understanding's edge, pointing toward territory not yet mapped. Why these questions matter extends beyond abstract theoretical interest. If we could understand why vacuum energy runs so small, practical questions in physics would change character. Black hole interior nature, currently described as singularities where space-time curvature becomes infinite, might look entirely different. Singularities might not be genuine reality features, but artifacts of using descriptions where they break down, like describing water waves using equations assuming water is continuous rather than made of molecules. The early universe poses similar questions. Standard cosmology describes the Big Bang as singularity, a point where space-time itself began. If our understanding of vacuum energy and gravity changes, the Big Bang might not represent reality's beginning, but rather transition to a phase where certain descriptions become valid, with something else preceding it. Understanding the vacuum energy problem might connect to the hierarchy problem, the puzzle of why the Higgs mass runs so much lighter than Planck scale. These problems share mathematical structure. Solving one might illuminate the other. Practical technologies remain distant, but history shows abstract understanding eventually connects to applications. Einstein's relativity seemed purely theoretical in 1905, yet GPS satellites today require relativistic corrections for accuracy. Quantum mechanics seemed purely philosophical in the 1920s, yet modern electronics, lasers, and medical imaging all depend on quantum effects. Understanding vacuum energy might eventually enable technologies we cannot currently imagine. The timeline for such developments, if they ever occur, stretches far into the future. What we have now is beginning of understanding, a glimpse that vacuum energy carries mysteries we cannot yet resolve. Understanding why information appears so central to modern physics illuminates research direction. The vacuum catastrophe sits at the intersection of our two most powerful physical frameworks, quantum mechanics and general relativity. Wherever these frameworks meet, interesting things happen. The vacuum catastrophe is one of the most dramatic examples. Classical physics treats space as passive arena where things happen. Quantum mechanics reveals space is not passive but seething with fluctuations. General relativity reveals space is not fixed but dynamical, responding to energy and matter. Combining these insights produces tension. Quantum fluctuations carry energy. Dynamical spacetime responds to energy. The response should be dramatic. Yet, we observe near placidity. Something resolves this tension. We do not know what. Finding out would advance physics in ways hard to predict. The history of such advances shows they often exceed initial expectations. Newton's gravity united terrestrial and celestial mechanics. Einstein's relativity united space and time, matter and energy. Quantum mechanics united waves and particles. Each unification revealed unexpected connections and enabled unexpected applications. The next unification, whatever resolves the vacuum catastrophe, might reveal equally unexpected connections. We wait to discover what they are. The vacuum catastrophe occupies a unique physics position. It is not small technical problem awaiting clever calculation. It is not discrepancy that might vanish with better measurements. It is fundamental conflict between two modern physics pillars when combined. Quantum field theory tells us vacuum has energy. General relativity tells us energy curves space-time. Together, they predict a universe radically different from the one we observe. So, something is deeply wrong with how we connect these frameworks. This is both discouraging and exhilarating. Discouraging because it means our best theories are incomplete in profound ways. Exhilarating because such fundamental problems have historically led to revolutionary advances. Newton's mechanics was incomplete. It could not explain light's motion, atoms' behavior, or Mercury's orbital precession. These failures led to relativity and quantum mechanics, expanding human understanding dramatically. Perhaps the vacuum catastrophe points to similar expansion. Perhaps the theory resolving it will reveal nature aspects currently hidden from us. Perhaps the next physicist generation will look back on the vacuum catastrophe the way we look back on black body radiation's ultraviolet catastrophe, as signpost leading to a new era. Or perhaps the problem will remain unsolved, a permanent reminder that some questions exceed human capacity to answer. Science offers no guarantees. What we can say is the problem is real, the discrepancy is enormous, and resolution remains unknown. The vacuum, that seeming nothing between particles, holds one of nature's deepest puzzles. Looking at empty space, you are looking at something quantum mechanics says should contain colossal energy, that general relativity says should curve space-time dramatically, but that observations reveal as nearly placid. The gap between what theory predicts and what nature delivers is the largest in all of science. That gap is the vacuum catastrophe. Understanding why it exists would transform physics understanding. We wait for that transformation. Let me bring this exploration to a close. We started with a number, 10 to the 120, the factor by which our best theoretical prediction overshoots observation for vacuum energy of space. This is not small discrepancy. It is the largest mismatch between theory and observation in physics history. The vacuum, which we casually call empty space, teems with quantum fluctuations. Each mode of each quantum field contributes to vacuum energy. Sum those contributions with reasonable cutoff, and you get a number enormously larger than what cosmic expansion observations imply. This matters because vacuum energy gravitates. Unlike ordinary quantum field theory, where you can shift energy zero without consequence, gravity responds to absolute energy density. Vacuum energy should curve space-time, should drive cosmic expansion or contraction. If the theoretical prediction were correct, the universe would expand so rapidly no structures could form. No galaxies, no stars, no planets, no observers to contemplate the problem. Our existence places upper limit on vacuum energy, and that limit runs 120 orders of magnitude below what naive calculations suggest. Something suppresses the vacuum energy. Something cancels it or hides it or prevents gravity from responding to it. Decades of effort by brilliant physicists have not identified what that something is. The Vacuum Catastrophe connects laboratory physics to cosmic physics. The Casimir Effect, measurable in tabletop experiments, demonstrates vacuum fluctuations produce real forces. Accelerating universal expansion, measured through distant supernovae and cosmic microwave background, demonstrates something like a cosmological constant exists. The same equations apply at both scales. And at the interface, where quantum fluctuations meet cosmic expansion, equations fail to match by incomprehensible margin. This is where physics stands. Remarkable successes in understanding particles and forces. Remarkable successes in mapping the cosmos. At the junction, a puzzle defying resolution. The next breakthrough might come from quantum gravity. It might come from new observations revealing dark energy is not simple cosmological constant. It might come from symmetry or mechanism nobody has yet imagined. Or it might remain unsolved, permanent marker of human understanding limits. What we can say is the universe permits our existence, despite this theoretical catastrophe. Vacuum energy, whatever suppresses it, allows galaxies to form, stars to shine, planets to coalesce, and life to emerge. We find ourselves in conditions compatible with complexity, even though our best theories say those conditions should not exist. Thank you for taking this journey with me through one of physics' deepest puzzles. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, resting in a vacuum whose energy, for reasons we do not understand, permits the existence of everything you know. Good night.